Okay, so choice of language is critical, and of course it depends on people to people, person to person. Uh, this is my personal perspective. So just to give a background, that a lot of people use Fortran in scientific computing even now, but there is a now significant number of scientists and engineers who use C and C++, not Java. Java is bulky, so Java is not used for scientific computing. And Python is also used. Fortran, one reason why it is used is that people learned Fortran as a language when they were young. So actually, there is also a divide. Older generation tends to use Fortran, and the newer generation now is tending to shift to C, C++. And Python, of course, everybody needs to know now. I mean, it has become important for things other than just programming for scientific thing, like visualization. That's part of scientific in some sense, right? Post processing, simple data analysis, and machine learning. Machine learning, Python has become a de facto language. Okay, so Python is must for everyone. Actually, I think I strongly recommend that everyone. Well, most of you know already, but some of you are not knowing it. Please learn it. So basically, it boils down to Fortran or C or C++. So it's Fortran, by the way, it started somewhere in 1960s, and this is called formula translation. This is the translate. There is a short form for formula translation, Fortran, and this was to use of one of the early machines, some of the early machines. So people wrote that compiler, and of course, that what Fortran we see today is very different than what it was for the first time. It's advanced and it is modern, but Fortran does not offer that object-oriented features, which was part of C++. Now, before we go to C++, I think C is very similar to Fortran, but C was started for making the operating system. In fact, it started in Bell Labs, as I said. To There were problems. There was no uniformity in operating system. They were not portable. So if you write in assembly level language with this operating system, then it is only for that machine, not for other machine, right? Because it is using that machine, rather the instructions of that particular CPU. So compilers were the operating system was written first time in higher level language by Bell Labs researchers, Carnegie, um, no, not Carnegie, Cunningham, Pike, whole team, Ritchie, and they wrote this operating system. It's amazing that it is written in a new language itself. Okay, so in fact, one important point is the Unix had the first Unix had only 800 lines of object assembly level code. Rest of it was in C. So Unix by itself is a beautiful thing. So you should like to see the philosophy of Unix, how it was designed, and what are the uh, what is the philosophy of C, and Unix is very important. In any case, C and Fortran are roughly equal, but except C had a strong support for integers, not so much for float, which is again a bottleneck for research scientists and engineers. But libraries were written. Now C is as good as Fortran if you use the proper library. Okay, but then C++ came, and C++ has a very interesting feature of objects. And the analogy I can make is when you read a book, no, you read the chapter wise. There is certain theme of the book, and if you try to read book, I mean, nobody reads book character by character. No, you read word by word, if at all. In fact, sentences we never read word by word. Now there's a research. So supposedly we read the whole sentence almost in one shot. You don't. Children read correct word by word, but grown-ups read in somewhat collectively. So all, I mean, so this is an analogy. So objects were created. So you can have object like chapter. which is not possible in C. C, the data types were primitive, and also you don't have functions associated with the data. So objects, the important point is that you have associated functions along with the data itself. So data plus associated function, that makes it an object. So I can have array in C, or we can have reasonably sophisticated data structures in C. Trees are possible, but then associated functions are not in C, not written in C. That feature doesn't exist. So given an array, I can write, okay, so I know that it's a vector array, then I can say what is the curl of the vector, divergence of a vector, and that becomes part of the package. And we use it in our programs. So we have associated functions. What is the nonlinear term given a vector? So u dot grad u is a part of that object. I don't need to say, well, u dot grad is a separate function. It's part of that object. U is a velocity field, like for Navier-Stokes solver. So that feature allows C++ to think in an abstract manner, is in a bigger manner. So now I've been really thinking, so I make an aside remark that not everything can be understood by just basic building blocks or basic forces. People say that, okay, we understand fundamental forces, we understand everything. No, I am not a believer of this. Not only me, there are many people who don't believe this. There are laws which are multi-scale laws, and they determine a lot of macroscopic properties. Okay. Anyway, so this is in the same line. So I really like it philosophically. As I said, we don't listen to music by seeing waves of a sound. It is collective which gives you a feeling of things. Anyway, so I just wanted to say that these are important things to think also philosophically. And in fact, there's a lot of things in programming is thought in an abstract manner, in a bigger manner. When people think of algorithms, they don't think of bits and pieces. They think really about larger ideas. And you need to think about it. I mean, here when you say programming, parallel programs, you really need to abstract your thoughts. Okay, so I think I wanted to add this today, so you just get an idea how to solve large problems. And C++ is really one of the most important languages of today. Of course, Java too, but Java is for more of web stuff. So it is not. So there are different domains: Java, PHP. That's for web developments. Okay. So one more thing. So these are the standard thing which I said. So C++ float is again weak, and even array operations are weak compared to Fortran. But now there are packages which you should use. So you really should use libraries. Now Python versus C++, I would like to just say a few comments which are important. In fact, we are going to use Python in this course. It's somewhat strange, that scientific computing, HPC are using Python. So, but people are using it in the world. So we just want to learn some of those tools and communicate to you. So it's slower than C++, but coding is fast. So there are estimates that we can write a code 10 to 100 times faster in Python. Okay. Testing is also very easy. Since it is interpreted language, you can test piece by piece, and you can really get your work done very quickly. And also it has very strong library. So a lot of libraries exist. I don't need to write a code for ODE solver. The solver exists in Python. So I just use this library, like linear algebra. C++ libraries also exist, but it is very easy to do in Python. Eigen values, just straightforward, one line, and very intuitive. Okay, so it's fast. That's why. Now it turns out we can write a parallel code in Python. Okay, that's what we'll do in this course. So we need this MPI library for Python, which I'm going to tell you how to download. Well, not how to download will be put on the web page, but which library you should download. Okay, so that you'll need it for Python in your laptop. But of course, laptop is only for illustration. But you can do it in a server. You can put a Python server, Python in your server, and you can make it parallel. I mean, you can run parallel in a server, and we'll do some of it in our server. Okay, and so another point is in Python we can call efficient libraries. So though Python code is slow, but FFT of Python is as fast as a C when you call in C program, because Python will call the optimized C library. So the FFT part takes same time in Python as in the C code. I hope this is clear. If not, then you can ask me. It's a function. When Python calls a function, it runs an object code which was compiled using C. It was a C code which was compiled. So remember, we gave a control. So when you call a function, it is basically starts running an object code. So it is same object code which will be running when you call from Python or from C. So it is going to be equally fast in both the platforms. Okay, so that is the idea at present. In fact, we don't need to write a C code for the whole program, whole problem, but we can write in Python. But for most time-consuming things, you have C libraries. Rest all you work with Python, because you can very effectively manage your code in Python.
So,
Yes.
so I had a small confusion. So
Okay.
for this FFT, do you mean to say that we need to import something from C into Python, or does the built-in function for Python itself access the C code?
Okay, very good question. So for FFT, is an example. FFT already is packaged in Python, standard Python. So it's an import FFTW. So it will import it, just like import NumPy. No, you say import NumPy. So it will import FFTW library, which is C object, in fact. Okay. Now you can also write your own C code, make it parallel or make it very efficient, and then you can make a package, like then import that package.
Okay, sir.
Okay, so you can make your own library for Python, then import it when when you start your Python code.
Okay, sir.
Import is the thing. I mean, import any library you like. It could be standard library or made by you yourself. All right.
Okay, sir.
Okay. Thank you. Okay. Now compilers, as I said, this I covered it last time. GNU is free and is also very popular. And these are new things which are coming, but they are not fast actually. They are for compilation, and that's various platforms. So we'll not get into that. These are not free. Intel compilers, PGA compilers, NVIDIA compilers, all this. Okay. So so some hardware which are made by a particular company, like NVIDIA is making this hardware. So some of the compilers may be better for that hardware because they know the hardware well. No, so we will try this NVIDIA compiler for GPU, and we'll know. I mean, I right now I don't know how good they are, but we'll see. Okay. Um, so AMD has its own compiler which we have not tested, but this for Rome processor, it may be better than standard GCC. But the GCC is a huge workforce. Huh? There are really volunteers who contribute to this stuff, making GCC, making the compilers and many libraries. Okay, now MPI and OpenMP. Okay, OpenMP is a platform which is for shared memory. I told that before. So these are now part of the language. So GCC, when you install it in your machine, using GCC, you can run OpenMP. Okay, that's so there are options. You just say compile this with OpenMP, and it is quite straightforward. We'll show you all that stuff. It's just a compiler option for OpenMP. Is there in Intel? So you don't need a separate library. It's coming as part of the compiler itself. You just need to put that option. Now MPI also comes with basically MPI has to be installed often. So there are free ones which we recommend that you install in your laptop or desktop. Well, mostly I think you are using your laptop. OpenMPI and MPI CS3. These are two free ones I know of. There are some more, okay. But MPI CS3 is what we'll use in this course. Okay, it's free. You can download it, and Somdeep is going to help us in putting a instruction how to install in your laptop. So learn how to install it, because you'll get a new machine, in your lab, your research lab, uh, and then you should know how to install this libraries. Okay, so even though some of it is available in Computer Center HPC 2010, where you will do a lot of homework, but please learn how to install this library, and it is straightforward. But you'll just get confidence that I can install it. That's about it. It's just thing. Sometimes if your thing system is not set properly, it may give problems. Then we'll see how to help you with that. There are other MPIs which are not free, which are part of like Intel. Well, Intel MPI is somewhat free for academic license. You have to just register it and you can get it for free. Cray, no, Cray is runs only on Cray machines, and it is not free. Okay, so as I said, please install MPI CS3, and also for MPI in Python, we need this library. Oh, I'm sorry, I forgot. PY, not mid error. MPI for PY. So this one requires MPI CS3. So Somdeep Felder helped many of us to install this yesterday in your laptops. So you need to install this first. For that, you need some compiler, okay, some C compiler, and then we can install this one. Okay, so we'll put up instructions how to do it, and I'll send you the link for that instruction, and then you can install them. Okay, testing is very critical, because first time the code is never, well, I can't say never, but sometimes if you're lucky, you can get the correct code first time when you write it. But often there are bugs, errors, and bugs means errors. Huh? So there is again a history why it was called bug. So let me just tell you why it is called bug. Anyone knows why it is called a bug? So earlier, this wall tubes were used for making computer, and it did invite a lot of insects, bugs actually, and that will make it malfunction, make those things. So they have to clean these bugs. They have to remove those insects. So that's why they're called bugs. So the thing is to test it thoroughly, uh, remove all your bugs, okay, and test. So how do you test it? I mean, suppose I write a code for weather solver. So well, weather is more complicated, but Navier-Stokes solver, okay, that's what we do in our lab. So there are some exact results. So you say, well, if I have certain type of velocity field, then how does it evolve? It's function of time. Or for sure, for Poisson solver or for Laplace equation, we exactly know what is the solution. You can put two charged particles, we can compute the potential. We know what is potential for two charged particles. So exact solutions are known, and you should do that first before you do for n charged particles, or for complicated potentials, boundary conditions. Okay, so always test with some exact results which are most often available. Okay, limiting cases. So it turns out your code works for many cases, but limiting cases it fails, because limiting cases, sometimes you've forgotten how to, like, you don't start with I equal to 0 or some bug. Limiting cases are things one should really test. And also it helps, I mean, keep in mind that exact results, limiting cases, then you're always, well, let me test it out. So for fluid solvers, viscosity 0, kinetic energy must be conserved, and we test it, see whether it is conserved. And this is how we test our codes. Keep testing frequently. Maybe these two tests will, well, by the way, these two test passes doesn't mean that your code is correct. These are limiting cases. Your code may not be correct for a general situation. Okay, so that bug will come some time later, and that you have to keep testing, and you have to keep correcting them. That's how codes have good codes have lifetimes of 40 years, 50 years. Many codes written some 1960s, 70s are still being used. Well, of course they are kind of polished and so on, but old codes are also there right now. Okay, now versioning is an important thing. As I think I mentioned this before, the GitHub is a place where you can, is a free repository. It's called repository, repo. So you put your files in that GitHub. Well, you put your program in GitHub. So there are lots of files, and you can push it. There are ways to push it, straightforward, and so you maintain it. So because sometimes your disk, well, you should also back up your hard disk. No? So sometimes the disk will crash, then you lost your all your efforts of years of work. So it's good idea to back it up as well as put in a GitHub. In fact, GitHub, yeah, I mean, these platforms will stay for long time. Like Google is not going to crash. So, so GitHub is a good place. It's free right now for academic work, and you can put your codes and version them. Version is, so when I make a change in the code, like I fixed a bug, then you don't replace your old code. Let it be, and you just say that I fixed this bug and push it. So in fact, it puts a date. So this date, this was the code. This date, this code was there, and with this change, then you have a track which file you changed and what was the change made. Maybe your change was not accurate, so then you can fix it further in a future development. So versioning is important, and keep track of when changes were made, who made the changes. You have to give credit to people who contribute to the code. So all that is done, and these are the platforms which host Linux and various, I mean, big developments are hosted in this platforms. There's another one called Bitbucket, and I'm sure there are many more, but most people use GitHub. I know Bitbucket we used to use before, but now we moved to GitHub. It has a easier interface compared to Bitbucket. At least that's my opinion. Now building codes. So our code has something like 100 files. Now I want to compile this 100 files, and some files, well, 100 files are not compiled simultaneously. Some files are compiled first, then second, third, fourth. But if the third file imports something of file 1, then I can't start with file 3. File 3 has to be compiled after file 1. So there are sequence of files which have to be compiled one after the other. Okay, in objects, there are some small objects and big objects which use of the structure of small objects. So there is sequence we have to compile, and some of this is done by packages again. There are nice tool called CMake, and there's also called Makefile. So CMake is what we use. So this is a nice tool for compiling and building. So you get an object file, no? But if you just try to compile this 50 of them manually, is just cumbersome, and you make some changes, and again you have to follow that procedure. So CMake, these are the files these are tools which are used for compiling, and I think I will not tell you all this stuff, but you can learn them by Google it, and start using it, then you'll learn it. Okay, so open or closed. So should you make a closed source program or open source? Of course, all the industrial companies like Apple and so on, they have closed source code. So I can't get a Seek version of their operating system, right? It is, you get only a object code, which is there. Okay, so these companies make money because it's disclosed. Nobody can see them, and they only can sell. But in academia, there is some people keep it closed. They don't share it, and they just do. But there is a large number of people who use open source. That means the source code will make it available. Like as I said, the MPI CS3 is open source. Anybody can download it, use it. Our libraries are also open source. I mean, our code is there in the website for download. So which one should you do? I mean, of course, some people say, well, I put all the labor, so why should I share with others, right? I mean, But it turns out, well, some of it is social work. I mean, it's just that you build a group. Somebody may just use it and come back to you, say, well, nice thing. So it's also social work. So you're contributing to knowledge. The Linux development is unselfish work, so you're doing it, of course, for fun, but it's for public. But it's also nice that when some people use the code, they find some bugs, and often they come back to you saying that this was wrong, and either they'll ask you to fix it or they'll fix it themselves. So if somebody tests it and says this is a bug, this is good for you, no? I mean, so somebody has tested and told me a bug. So we use it to our advantage. Somebody says, well, this is a bug. So we fix it, and yeah. So it helps. It has its own advantages to keep it open source. But yeah, it also build groups. People come and collaborate. So this is, I think, I prefer that academic code should be, well, if you have to decide, my vote would be go for open source. Uh, that's one. Second thing is, there's some codes which are both open and both closed, open as well as closed. That's a contradiction, right? But so some version is open, like OpenFOAM is a big software for fluid solver. Some version is open, but some version is closed, which is advanced version and so on. That's one feature. Second one thing is, these companies, of course, have to survive. No, they hire people, so they have to pay their salaries. So the one thing they do is, for support they charge money. Red Hat Linux is not free. So this for servers, HPC systems. So for support, they'll say, well, every year you have to pay us this much money if you want support. Okay, so in fact, Red Hat is not, I don't think you can get a source code for that. So it has closed. So support they ask. So that there are various versions. I mean, I think we don't need to discuss it, but I just wanted to mention it here. Their licensing, suppose you make it open source, then there are various types of licensing, BSD, GPL, and so on. You need to worry because you don't want to just leave it like that. In fact, you have to say that you have to acknowledge this code if you use it. So there are various license schemes. Okay, it's free, but still you have to put a license scheme. Okay, well, I mean, I will not get into it. Somebody wants to know, then I will tell later. Now, I just want to say that I'll give an example. The code we developed. So this from my personal perspective. That's why I can say what are the pitfalls, what happened. So I just wanted to go through it once with you. So this is a code I started in 2003, in fact. So it took me a year to design it, more than a year actually. 2 years I was teaching and other work, so on. So I was thinking about it really to build it a very nice code. The reason why I thought about it, that when students write, when the student graduates, then the code, I don't have control over the code. I don't know what is there inside the code. So the idea was that we have a code which everybody knows what is inside the code, and is written in such a way that it's easy to read. It can do more things. So our code, in fact, is a unique code in the world, which can do many things by just using objects. So it can do fluid, it can do magnetohydrodynamic, convection, rotation, huge amount of things, okay, and different boundary conditions. And that became possible because I used objects. Well, right now there are more developers, so I should acknowledge, like Anando is, I think he's there in the audience. Somdev is contributing. There are other students who tested, contributed parts of it. So it's a team effort, and that's why if you have a bigger vision or it's a dream in your mind, then people will contribute and people will make it richer. And of course, not only here, there are many groups. Well, many, I can't say, several groups in the world use it. Okay, so it took me more than a year, and I learned C++ that time. So that's when I said I wanted a general code. Then okay, this is how it offers. So I started doing it. And unfortunately, in IIT, there are not many people who write parallel codes, especially the large parallel codes. Okay, small ones people write. So all this stuff like CMake, some of it I learned from friends, but a lot of it is Google, Google heavily. So FFT, I had to really use MPI. I got some help from when I visited Brussels. They're very good friends. In fact, I can just say this. When I talked to my friend Daniel Karati, he said, "Oh, MPI is very easy. You need to only know 6 things." In fact, yeah. So one library is to send, to receive, to sum the data in different processors. In fact, indeed, MPI is pretty trivial actually. Once you know how to use it, uh, so that's why you don't need to be saying, "Well, why are we not studying MPI in this course?" This is very trivial. Once you get an idea, they are just functions. You call them. You get bugs. Debugging a parallel code is a problem. Calling these functions is straightforward, no problem at all. So using them correctly is a issue. Okay. So I'm grateful, of course, to many people. So, but Google is a good resource right now. Okay. So you can just find, and people have really written nicely, and I think that's where we should also contribute in terms of how to's and pitfalls and so on. So this course, I believe I'm trying to contribute to this community. Okay, so make the code better and better. So the code we started in 2004, we have revised some 30 odd times. Okay, it has been, sometimes it has been basically trashed, rewritten. And I can say that this is the best spectral code, I can say with certain confidence, in the world. Okay, so it was really designed well and it can do many things. And hunt for hardware. So in India, again, hardware is not very easily available. But once you have code, then in fact those companies come to you. Okay, they say, "Well, we want to use your code to test it." There are very few codes which run on the whole machine. So how will they know that whole machine works together is on a single code? In fact, we are invited by, like, Saudi Arabia wanted to use our code, the cows. So just to test how things are with our code. So this is machine in Kaust. And since we had the code, we could, well, of course, I had to request and so on. It's not straightforward that they'll say, come. So you have to just work with them, but then you can get access to the best machine. ICA was number 4 machine, as I had told before. This machine, we got access reasonably easily. So, but there was some issue later, and this machine was, of course, shut down. Param UA we used for free. Huh? So these are all for free. These are the developers right now, and there's just said lots of students contributed to this. But so that is why we should have a long-term objective. That's what I would like to say to young people, young students, uh, and then it builds up. It just builds up over time. Okay. So there's a award which came. So there's a blog I wrote actually. That's the reason I. So this blog you may find it interesting. So I summarized it right now. But so the reason why I wanted to bring it up is that large codes require decades of effort, not years of effort, decades of efforts. And if you have big plan, then it materializes. Okay. And based on this code, we are writing another code for finite difference, which is already running, but we need to optimize it, and we are quite a bit of work is left. Okay, so teamwork is very important. So we build a core team. Sometimes you have to start alone. Most often you have to start alone, but then people come together. Part-time developers, testers, user, documenters. So you have to find out who will contribute where, and then things build up. Okay, advertise is another important point. Write a good manual. Unfortunately, we don't have good manual. A good website, social media, conduct workshops. We did some of it, but not. I mean, I think these are issues which we are not very good at it right now. Lack of manpower, skills. Okay, so if you are writing a code, then you need to do this, and you should write a code. Actually, I would say, and spread word around. Okay, exercise skill challenge. I wanted to say. So now there is a call for writing codes which are run on these big machines, which can compute 10 power 18 operations per second. Okay. Now there's no code. Well, first of all, the machine doesn't exist, but the very few code we run on a petascale machine. Very few. I don't mean to say one or two, but there are handful of codes. Um, Maybe I don't think more than 50 codes run on petascale machine in the world. Okay. This it requires a huge amount of engineering within the code. So we need well-designed program, optimized, correct, tested, very good hardware, and so and this hardware keeps changing rapidly. Even software, this MPIs, new compilers, newer. So this field is also very interesting because it changes every 6 months. Things are changing, but also very challenging because you have to uh, keep at it. You can't if you lax, then your software gets outdated or your hardware gets outdated. So this paper you may like to read is there in my website. So I kind of very simple way I wanted to communicate what are the challenges for exascale computing.